Welcome to the Strength of Materials course. We are in the first week of this course. So the first week is all about mechanical properties of engineering materials. Mechanical properties are physical properties that are exhibited by the materials upon the application of forces on them. We will also focus on strength of a material, wherein strength of a material is its ability to resist loads without breaking or deforming excessively. We will also see how to quantify it and the different measurement methods. In this session, we will be looking at the following topics. Our session starts with strength of materials, definition for strength of materials, and then we'll look into the basics of strength of materials. We'll go through simple stresses and simple strains. We'll establish the definition for stiffness of materials. Later, we'll go through material properties. We'll establish a connection between load deformation diagram, which is basically stiffness, with material properties, and stress and strain diagram, which is basically Young's modulus with the material properties. Next, we'll understand how to read stress strain graphs. Then we'll see about Poisson's ratio and then end our session with shear stress and strain. The learning objectives for this session is that we'll first try to understand the mechanical behavior of materials in engineering sense, which is very important. We'll then try to define the term strength of a material. We'll use this term as we progress with the course. Then we'll try to understand the types of simple stresses. So these simple stresses that can be applied on the structural elements. Next, we'll try to understand the term strain, which is basically how materials deform under stress. Next, we will try to establish a relation between stress and strain, which is the Young's modulus, and we'll also work through some problems. Finally, we'll try to end the session with an overview of Poisson's ratio and shear stress and strain. What is strength of material? Strength of a material is a major factor during the selection of materials for engineering purposes. It is the capacity of a material to carry or resist loads. For example, an ant can lift 10 to 15 times its own weight. Some species like the Asian beaver ant can even lift up to 100 times its own weight. So, an ant can be said to have such high strength. Sparing the above said example, usually loads can be of different types. They are tensile, shear, flexure or torsional loads. Since we are engineers, we are more interested in the strength of a material in engineering terms. In engineering terms, it is a calculation of stress and strain in structural components. The strength of a material is affected by two major factors. First are the mechanical properties of the material. These are the properties that involve a reaction to an applied load. Second are geometrical properties. These are derived from the geometry of a solid body or particle. So basically these are derived from the properties that are affected by shape and size. Now coming to some of the important mechanical properties, the first one would be strength. Strength of a material is its ability to withstand an applied load without failure or excessive plastic deformation. Next is stiffness. Stiffness is the ability of a material to resist deformation. Toughness is the amount of energy per unit volume that a material can absorb before rupturing. Finally, hardness is defined as a material's ability to withstand localized permanent deformation. Next, let's look at geometrical properties. The first property is volume. The strength of a material increases either when the structure is very small or when only a small volume is under strain. So, a smaller sized material is stronger relative to its volume. However, strength is also dependent on other factors like orientation of the material. Example, material with higher length, weight and thickness has higher strength. These are the dimensions like length, width and thickness of the material. Then we have boundary conditions. Boundary conditions can also be called as boundary constraints. So this is the way the material is supported before a load is applied on it. Finally, we have changes in the geometry, which is the changes that a material undergo due to load applied or environmental effects. Here also the strength of a material can also change. So for this, as an example, the cross section of a steel rod in tension reduces and thus reduces the amount of strength the rod can take. Now let us look at simple stresses. Stress is the intensity of a force on a solid. Let's start with the basic type of stresses that are found in materials when they are under a load. To understand simple stresses, one of the simplest types of loads that can be applied on an object is tensile loading. Let's consider a uniform cylinder that is pulled apart by a force applied on the either ends. The thickness of the cylinder will get reduced at the center and the material will eventually break apart. The force that is applied on the cylinder is F, depicted in kilonewtons, and A is the cross-sectional area. Stress, which is sigma, is equal to F divided by the cross-sectional area A. Thus, stress is affected by the force and area. Higher force applied on the material implies that there is a higher stress on the material, and when cross-sectional area is higher, the stress on the material is lower, since area is inversely proportional to stress. Thus, in this case, the stress on object A, which will be higher than, thus in this case, the stress for the object which has lower cross-sectional area will be higher than on the object which has higher cross-sectional area, but provided all the other conditions remain the same. Commonly used units of measurement for stress are kilonewton per meter square or Pascal. 1 megapascal is 1 MPa, which is equal to 1000 kilonewton per meter square. Another unit of measurement for stress is pounds per square inch or PSI. 1 megapascal is approximately equal to 145 PSI. Let's look at the difference between engineering stress and true stress. Engineering stress, that's sigma E, is equal to the applied load divided by the original cross section of the material. However, when a material is placed in tension, it shows a necking behavior, that is, the cross sectional area is reduced when it is under stress. This reduction continues as long as the material continues to be under stress. Thus, in reality, a different stress needs to be measured. This stress is called true stress or sigma T as given here. So, true stress is the applied load divided by the actual cross-sectional area A1 of the material. A1 is the changing area with time. Therefore, sigma T is calculated using the instantaneous change in area during the tensile test. Since A1 is always less than A during the test, the true stress is greater than the engineering stress. Sigma E or engineering stress is considered to be the average stress in the system. This is also called as nominal stress. However, it is very difficult to measure A1 as the test is being conducted. Thus, to simplify, we use A. Hence, we always calculate the engineering stress. Now, let us look at the types of stresses that can act on a body. First is normal stress. This stress acts along the direction of the force or the transverse direction. The first kind of stress is tensile stress. This is a stress that pulls apart an object. When under a tensile stress, the object will distort, that is, its dimensions and shape will change. An object under tension will elongate and undergo necking. And here, necking is the phenomenon where the cross-sectional area reduces. As this stress is increased, the material will break apart. The next type of stress is compressive stress. This is also a normal stress. Here, the force acts along the direction of the material. Compressive forces push the material together, and an object under compression will become shorter and begin to bolt. That is, the sides will distort by curving outwards and begin to bulge. This bulged portion will then break off as the load continues to be applied. The deformation caused by normal stress is always along the direction of the force. Normal stress is equal to force divided by the cross-sectional area of the material, as we discussed earlier. In the case of tensile forces, the object will elongate and reduce in cross-sectional area and eventually break. While in the case of compression, the material will become shorter and increase in cross-section area and eventually break. In both cases, the deformation occurs along the line of the force. The next type of stress is called as shear stress. Shear stress acts perpendicular to the material, that is in the longitudinal direction. It causes slippage along the planes parallel to the stress. Shear stress is depicted using tau, which is equal to the force divided by the cross-sectional area of the material. An object under shearing will bend and eventually break. The next type of force is torsion. Torsion is a twisting motion that is applied due to torque. It is a rotating moment that translates to shear stress. Thus, torsion is twisting or wrenching of a body by the exertion of forces that tend to turn one end or part along the longitudinal axis. As seen in this figure, the graphical representation shows us torsion. Here, the torsion is shown in violet and the radius in red. The force is in blue. So when a torque, which is a rotational equivalent of a linear force, is applied on a body, it twists as shown in the figure. Next figure shows us how the material is twisted. Now let's look at simple strains. Strain is the byproduct of stress being applied to an object, which can also be told as the physical manifestation of stress on an object. Similar to stresses, there are various kinds of strains. Now let's discuss simple strains. Strain is the measure of deformation due to loads. In simple terms, it is a measure of how much deformation occurs in an object when it is placed under a load. Let us assume a material which has an initial length of L0 or original length. This material is placed under a tensile force of F. Under this force, the material will elongate to L, which is the final length, and here L is equal to L0, which is the original length, plus delta L, which is the change in length. Thus, strain can be defined as the ratio of change in length to the original length. That is, it is a measure of amount of change in length with load. Strain can thus be defined as epsilon, which is equal to delta L, that is change in length, divided by L0, which is the original length. Since both delta L and L has the same units, it is a dimensionless unit. Now let us see the difference between engineering strain and true strain. Similar to engineering stress, we also have engineering strain, which is epsilon E. It is the elongation delta L divided by the original length or L0 of the material. When an object is placed in tension, it shows a necking behavior. That is, the cross section is reduced when it is stressed. This reduction continues as the material continues to be under stress. Thus, in reality, a difference strain needs to be measured. This difference strain that has to be measured is called as true strain, or can also be denoted as epsilon T, which is delta L divided by L1. L1 is the changing length with time of the material. Epsilon T, or true strain, is calculated using the instantaneous change in length during the tensile test, which is L1. Since L1 is always lesser than L0, epsilon T is always greater than epsilon E. Thus, true strain is lesser than engineering strain. Since it is very difficult to measure L1, we use engineering strain as the nominal measurement unit. Strains can also be classified based on the loading type. The first type of loading is tensile loading. In case of tensile loading, delta L is the amount of elongation. Thus, tensile strain is equal to the elongation delta L divided by the original length L0. Also, tensile strain is always positive. The next type of loading is compressive loading. In this case, delta L is the amount of shortening of the object. Thus, compressive strain is the reduction in length delta L divided by the original length L0. In the case of compressive loading, the compressive strain is negative. This is due to the reduction in length of the object. The next type of loading is shear loading. In the case of shear loading or shear strain, the object deforms in the longitudinal direction. Thus, delta L is the amount of bending shear strain. Therefore, it is the amount of bending delta L divided by L0, which is the original length of the object. Then we have volumetric strain. Volumetric strain is the ratio of change in volume to the original volume of the material divided by V0, which is the original strain of the material. Volumetric strain is equal to sum of strain in all directions. Thus, volumetric strain is equal to 3 times the linear strain that is on the material. Strain can also be classified based on the direction of deformation. Let us assume a material which has an initial length of L0 and an initial weight of B0. When this material is placed under a tensile load, it will reduce in cross section. This reduction is delta B. it will also elongate this. Elongation is delta L. Thus, the transverse strain, which is normal to the loading direction, is equal to delta V, which is the reduction in weight, divided by B naught, which is the original weight. Similarly, longitudinal strain is parallel to the loading direction. Thus, longitudinal strain is equal to delta L, which is elongation divided by L naught, which is the original length. Now, we can see some of the elastic behavior of materials. When it comes to mechanics of materials, countless number of scholars have made notable contributions in the field. The very important ones are elastic stiffness, which was given by Robert Hooke, who did the spring mass test. Then we have the material properties that was first introduced by Thomas Young, in which the first property being Young's modulus in 1810. Then we have the Poisson's ratio, which was introduced by Simon Poisson. First we'll start with the material properties and load deformation diagram, which is basically stiffness. Robert Hooke first introduced stiffness in 1648. The primary definition of material stiffness was provided by Robert Hooke, and his experimental method involved suspending a number of springs with masses measuring the deflection and respective extension. The diagram which you can see in the right side is an example of one of the systems that Robert Hooke presented. So in his experiment, he had a spring and a mass attached to the spring, and he calculated the deflection of that spring and how much is extending because of the mass. The force and the spring's extension are proportional to each other. So if we have a force on the mass, there will be an extension and then the spring will start extending. However, if we have an external force on it, the force will make the spring elongate, and elongation is directly proportional to the force that is applied. That was the experiment that Robert Hooke did. So when he suspended the mass and then put a load on it, he established the graph which is known as the load versus extension graph or load versus deflection graph. And he realized that the load is directly proportional to the extension of the system, or the extension is directly proportional to the load. So with the increase in load, extension linearly increases until a point which is known as the limit of proportionality, after which the linearity of the load extension graph goes away. And then we have a non-linear relationship. So basically the material goes into the non-linear field. So the elastic behavior of the material was first introduced by Robert Hooke, who said that there is a certain limit till which the material behaves elastically, and then after that the material stops behaving elastically. This is called as the Hooke's law. But after this material would experience plastic behavior. So from Hooke's finding, we can summarize that within the elastic limit, W is equal to K times U, which is the axial stiffness. Therefore, K is equal to W by U, and here K depends upon material properties and the geometry of the bar. Let's see an example to understand the K value for a system. In this problem, as you can see, a specimen with the diameter 13 mm and gauge length of 55 mm was tested under tensile loading, and the load versus elongation data is given. This data is ideally found in any experiment that is performed on the instrument or on the universal testing machine. So the load and elongation data is given, and we have to determine the stiffness of the material, which is the axial stiffness. We will use Excel to plot the graph, and then we will see how we can find the axial stiffness. The given graph here is the plot of the table we saw in the example question. In the graph, we can see that units for load and elongation are given as kilonewton and millimeter respectively, which is a very important information to note. We can also see that the linear climb is followed by a non-linear curve in the later stage of the plot. For better understanding, let us restrict our value of load till 41.9 kilonewton. This way we can concentrate on the linear range of the problem. After this line, the linearity has stopped, which means it has moved from linear to non-linear at that point. So we can say that this is the point where proportionality constant is met. K value is no longer linear or is the point of proportionality which we have seen in the graph as well. Hence, this is our limit of proportionality. Now we have to find the stiffness. Stiffness is nothing but the slope of the line of that linear region. To find the slope, we divide the load by the elongation, which is finally the formula to find stiffness, as we saw earlier. In this picture, we can see that the limit of proportionality is marked and the slope is actually calculated using formula for K. Now it should be noted that the K value is true only under the limit of proportionality. That means that any value that we get after load limit 35 kilonewton as per the plot does not fall under our range of stiffness. By this, the highest value of stiffness is for load value 12.1 kilonewton, which is 654.01 kilonewton per millimeter, and this is our final value of stiffness 2.